Real numbers. Chapter 2. Defining real numbers. So, real numbers, just like irrational numbers, negative numbers, rational numbers, those are all different types of numbers and categories of numbers that we will be introducing. And today we will be introducing real numbers. So, basically what we're trying to cover is what are real numbers and how can we even classify them. So learning goals, and there's 4 of them today. Understand the meaning of real numbers and classifying them. Learning the range of real numbers. Understand the one-to-one correspondence between real numbers and points on the number line. Able to use points on the number line to represent irrational numbers. So remember and think. Classify the following numbers into their own categories. So over here you are given 8 numbers and you have to classify them into rational or irrational. Okay. So for the first one, it has to be rational because it's already written in fraction form. A rational number's rule is if it can be written in a fraction form. This is not a perfect square. 3 is not a perfect square, so it's irrational. -4, it's negative square root of 4. It is rational because this is a perfect square. This is also rational. It is a determinate decimal. Any number including pi is irrational. This is rational because this is a perfect square. The answer is 8. This is supposed to be in the irrational area, and because this includes an irrational number, square root of 2 is irrational because 2 itself is not a perfect square. And since this goes on forever repeating, there's that little dot right there, it's rational, has a pattern, and it's irrational because while there is a pattern, it does not repeat. So classifying real numbers. Question 1. We know that rational numbers include integers and fractions. Notice how I use the word fractions. So all fractions are decimals, but not all decimals are fractions. So if you can think of it as this is a category of decimals, and fractions is a smaller circle inside it. It is called fractions. Okay, so going back to the lesson, you get this now. Use a calculator to write the following fractions in decimal form. What are their characteristics? So if you don't have a calculator, you could just quickly do some calculation on sheet of paper and pause the video. If you have a calculator, great. Just Alright, so let's look at their characteristics. So this 5 over 2 is equal to 2.5. Negative 3 over 5 is equal to negative 0.6. 27 over 4 is equal to 6.75. 11 over 9 is equal to 1.2. And 9 over 11 is equal to 0.81. And this has these 2 dots on it, which means that it is a repeating decimal. They can all be transformed either into determinate or recurring decimals. Now a recap on what are recurring decimals. Recurring decimals are just decimals that go on forever, but there is a repeating but it repeats. So for example, this. There's a pattern to this, so it repeats. Can integers be written as decimals? Can 3 be regarded as 3.0? So the answer to that is yes. So think, what conclusion can you get? Well, rational numbers can be transformed into finite decimals or recurring decimal forms. Conversely, any finite decimal or infinite loop decimal is also a rational number. So think, can all numbers be written in the form of finite decimals and infinite loop decimals, like the square root of 2, which equals 1.414213, and the cubic root of 5, which is equal to 17099759466, and so on. Well, actually, this number, like pi, or this number, which there are 1 more 0 in turn between two ones, non-recurring decimals, which are which like infinite decimals, but they don't repeat. For example, this, it goes on infinitely, but there is no pattern in here. Or there is a pattern, but it just doesn't repeat. The non-recurring decimals are irrational numbers. Think, is pi an irrational number? Is 1.0100100010001 and so on an irrational number? Well, they're both non-recurring decimals, so they're both irrational numbers. So numbers including pi, square roots of non-perfect square numbers, and non-recurring decimals are all rational numbers. So this is something worth writing down and taking notes on. Okay, think. We call rational numbers and irrational numbers collectively as real numbers. Can you classify real numbers? Okay, so this is something big right here. The whole part of this was real numbers, right? So even the title of this lesson is real numbers, and it includes rational numbers, and it also includes irrational numbers. So let's see the different ways how we can classify them. So the first one is by definition. So this is real numbers, and it splits into rational numbers and irrational numbers. Rational numbers, in which are determinate and they are recurring decimals, and irrational numbers are non-recurring decimals. Rational numbers further split into integers and fractions, while this is the squares of non-perfect squares, including pi, or pi itself, or just including pi, and non-recurring decimals. Now, what if it was pi over pi? That equals 1. So that actually would go into rational numbers. That's something that's kind of special. The other one that you should be careful of is the 0th power. So pi raised to the 0th power. So you might remember from last year that, or from the 7th grade math lessons, that any number that is raised to the 0th power always equals 1. And that's true for pi too. So it would also go into real rational numbers. So those are just two kind of, yeah, so that's just a exception. Try. Can you classify these following numbers? And this is going to be split into negative or positive. So in the positive, is the cube root of 2, 1/4, square root of 7, pi. And negative is negative 5 over 2, and then over here is square root of 2. Square root of 20 over 3, negative square root of 5, negative cubic root of 8, square root of 4 over 9, and 0.37337737773, and so on. So where does 0 go? Wow, this is very confused 0 over here. So what this means is that 0 does not go, it doesn't belong in here. So the number line, as we have learned last year in the lessons, the number line, right? This is 0. And, alright. So this part is 0. It has its own category. Yep, 0 is indeed a very special number. Up to this side are negative numbers, while up to the other side are positive numbers. So those are the two things to classify. And when you're classifying this, say on a on a test or homework or something, you could just say that 0 has its own category. It doesn't make sense to not classify it. Just mention that. So real numbers can also be split into negative real numbers, 0, and in negative real number. And then there is also, let me just pull this up. Okay. Alright, so this whole thing is up, and this is by properties. Real numbers can be split into negative and positive real numbers. So let's first look at negative real numbers. Oh, besides there's 0, so 0 just contains itself. This is the exact graph I just drew. Alright, so negative real numbers, it can be split into negative rational numbers and negative irrational numbers. Over here it's positive real numbers and positive rational numbers and positive irrational numbers. So this is kind of actually building on top of what we just had on the last slide. So in the range of real numbers, the meaning of opposite numbers, reciprocals, and absolute values still applies, as in, for example, square root of 2 and negative 2 are still opposites. The cubic root of 5 and 1 over the cubic root of 5 are reciprocals. And the square root of 3 is the absolute value of the square root of 3 is still the square root of 3. The square root of 0, the absolute value of 0 is still 0, and the absolute value of negative pi is still pi. So these the definitions of opposite numbers, reciprocals, and absolute values still applies to all real numbers. Now, this is not something we will be learning in middle school, I don't believe, or at least not yet. So these are all real numbers, and you might be thinking, so real numbers are all numbers. Why don't we just call it numbers? Why do we have to add real? Is there not real numbers? Well, actually there is, but not exactly called not real numbers. They're called imaginary numbers. One of which is the square root of negative 1, and that is also equal to I. You might have heard this before. This is not something, just quickly covering this in case you are confused on why we call it real numbers, because all squares of numbers has to be positive, right? Well, inside here, it is neither greater than 0 or equal to 0. This is smaller than 0. So this is what you will be introduced to in later grade levels. But just this is an example of an imaginary number. It's imaginary, not real. Question: what kind of operations can be performed within the range of irrational numbers? And does the following formulas hold true? So this is saying the square root of 2 times the square root of 5 is equal to the square root of 5 times the square root of 2. And as you can see, that is a commutative property over there. So actually, this is true. And right now it is saying that in order to solve this expression, we can first add our parentheses around here. And in the end, we get square root of 3. This is also correct. This is the associative property of multiplication. Trying to refresh your memories right there. And these are, this is 4 times the cube root of 2 and 7 plus 7 times the cube root of 2. You can factor 4 and 7 out, and then you will get 11 times the cubic root of 2. That is also correct, and that's the distributive property of multiplication. So what this is trying to tell you is that the laws of rational numbers still apply to all real numbers. It holds true in the whole range of real numbers. So what this is important is that we're starting to use this with radicals now, which in the next 3 lessons, which is going to be the last 3 lessons of this chapter, we will be focusing on how to simplify radical expressions, and these are all good things to just keep in mind when you're doing that. So yeah, we're going to be adding another set of numbers and irrational numbers. Example 1. Find the opposites, reciprocals, and absolute values of the following. Okay, did you find them? Shouldn't be that hard, is it? This is the answer. For the first number, the cubic root of negative 64, the opposite is just 4. And notice how I didn't just add a negative sign in front of it. I first simplified it. So when you're answering problems, you should be simplifying instead of just adding a negative sign in front of it. So it's first simplified. This becomes negative 4 at first, and then you take the opposite, which is 4. The reciprocal is negative 1 over 4. The absolute value is just 4. The number is the square root of 225. By this time, I suppose you have already memorized all of the squares starting from 1 all the way up to 20. So yeah, this is negative 15. Its reciprocal is 1 over 15, and the absolute value is 15. Alright, now the next number is the square root of 11. Well, it's opposite. This is the time when you can actually just plop a big fat negative sign in front of it because you cannot further simplify this. So this will be negative the square root of 11, and its reciprocal is 1 over the square root of 11, and its absolute value is just the square root of 11. The conclusion. If the number A is a real number, its opposite is just negative A, and its absolute value is the absolute value of A. That's how you would say it. And if A does not equal 0, then its reciprocal is 1 over A. Why do I have to say A is not 0? Because we can never have 0 on the bottom. It doesn't make sense. So, okay. Real numbers on the number line. Think. As shown in the figure, a circle with a diameter of 1 unit length rolls to right along the number axis from the origin. A point on the circle reaches point A from the origin. What is the number representing point A on the number axis? Because the circumference of the circle is pi, so the irrational number pi can be expressed on the number line. Think 2. Can you express the square root of 2 and negative square root of 2 on the number line as well? Okay. So here's the first. Cut and join two small squares with a side length of 1 to obtain a larger square. The side length of the large square is so that the diagonal of the smaller square with the side length 1 is. So these are the two small squares. And then you take 1/2 of that, 1/2 of that, and you just put them together as shown. So then you would have this shape. So what is the diagonal of each of the small squares? It would be the square of 1 plus the square of 1, which is 2, and then the square of that, which is the square root of 2. So that would fill in the blank right there. Okay, so those are equal. So if we draw a square right here, we have negative 2. We can slowly, so we first make a square with a side length of 1. The diagonal would be the square root of 2, right? Then we take that diagonal and we just kind of use a compass to put it down right here to set it down on the number line. So this point right here would be the point of square root of 2. And if you do it to the other direction, which is 180 degrees, that would be negative square root of 2. So every real number can be represented by a point on the number line. And in turn, each point on the number line represents a real number. So there is a one-to-one correspondence between real numbers and points on the number line. Example 3. As shown in the figure, the numbers represented by the 2 points A and B on the number axes are respectively square root of 2 and 5.1. So there are blank points representing integers between the 2 points A and B. And you have 4 options over here. Okay, so let's check our answers. Because the square root of 2 is about 1.414 and so on, so between the square root of 2 and 5.1, there are 2, 3, 4, 5. So there are a total of 4 integers between A and B, and C goes over there. So method conclusion, the points on the number line correspond to the real numbers 1 to 1. Combined with the number line analysis, you can easily draw down conclusions. Conclusions. Class summary. In real numbers, we learn all about the rational numbers and irrational numbers are collectively referred to as real numbers. In the real number range, the meaning of the opposite numbers, reciprocals, and absolute values is the exact same as the meaning of the opposite number, reciprocal, and absolute value in the rational number range. And the real numbers correspond to points on the number line 1 to 1. So each real number has a point on the number line. So we also covered the 4 skills of today. Understand the meaning of real numbers and classifying them. Learning the range of real numbers. Understand the one-to-one correspondence between real numbers and points on the number line. And the final one is able to use points on the number line to represent irrational numbers. So I hope you enjoyed the lesson for today. And in the next video, we will be learning about evaluating radical expressions.